Yeah, so hi everyone. For those people watching on YouTube later, that's my face. For the rest, or for all of you, I'll be speaking about rough terrain planning and navigation for legged robots, specifically for ANYmal. And this presentation will be kind of two-part. First, I'll do some kind of theoretical introduction to the method, and then I'll be speaking a bit about the DARPA challenge which we participated in last month. Well, yeah. So first of all, legged robots have made huge steps forward in terms of locomotion capabilities in recent years, largely through reinforcement learning and the robustness that those methods bring. And that, of course, necessitates also better navigation algorithms to make use of the capabilities that legged robots have. The biggest issue here is that traditional navigation approaches kind of assume that there's one specific traversability value, if you want to call it that, per terrain patch. So you assume, oh, this patch of terrain, the robot can just go or cannot go independent of orientation and such. That, of course, completely neglects the stepping capabilities that legged robots have. Ideally, what you want to do is, of course, full contact planning with all the kinematics and dynamics of the robot and do some kind of nice trajectory planning over the terrain. Unfortunately, currently, that's just not real-time capable. So we need something in between that can kind of take into account the capabilities of the robot while still being real-time capable. What we came up with, or what we use now, is a reachability-based abstraction of the robot. So what you do is you abstract the robot with two kinds of different volumes. You have a body collision volume, which encapsulates the main torso of the robot. And just like most navigation algorithms, you try to make this volume always collision-free. So you want to avoid touching anything with your torso because you don't want to hit stuff. And then where the feet come into play is we also have a foot reachability volume. The idea here is that we can kind of approximate the range of the feet and the reachability of the feet, and then enforce that these volumes always need to be in contact, because the robot needs to be in contact with the ground to locomote, because it's a ground robot, a legged robot, it needs to produce forces on the environment to locomote. So those are the two constraints we have. The body always needs to be collision-free, and the feet always need to be in contact. We do a couple of things to make this actually work well in real life. One of those is we learn templates for what steppable geometry is, because in a very naive version, the feet could also be in contact with, let's say, a wall, and then the robot would do a Spider-Man walk up the wall, which of course is not possible in real life. So we learn what steppable geometry is. We use a lazy PRM star-based planner, but we have a custom graph expansion scheme. What lazy PRM star does, it builds a roadmap, a planning roadmap, but it doesn't always check all the edges inside of the graph that it builds. It only checks the edges when you query a certain path in there. But that has some issues with accumulating graph edges that just never get checked, but are all completely wrong, which occasionally can lead to very long planning times. And then the robot just stands for a minute and doesn't do anything. So we work around that with our graph expansion scheme. And then we also do density-based and map-enhanced sampling, because we want to avoid drawing a lot of samples in just nonsensical regions or regions where we already have lots of information from prior samples. So learning foothold scores. We plan on an elevation map. So we have a grid around the robot, which has per cell the local elevation of the terrain. And this map moves with the robot. So yeah, it always stays centered at the robot, and you have the local terrain information around the robot. And we do learning in a very shallow neural network. And we call it template learning because really it's not really deep learning. There are barely any nonlinearities, and it's just 2 layers. So, but the implementation is as a convolutional network. So in the first step, we feed the elevation map through 3x3 convolutions with different dilations, just to get a bit of a robustness to scale. And you can see here the actual kernels that we trained here. And if you're used to looking at this, then you can see that those are kind of edge and corner detectors. So it learns pretty generic things that then also can transfer well between environments. Yeah, very basic things, but they turn out to be quite robust. And we enforce these kernels to be zero sum, mostly just because that makes them height invariant. If they're zero sum, you don't care if it's it's independent to height, because you don't care whether you're at sea level or on a mountain. The flat ground is the flat ground, so the absolute height should not matter. Then we take the absolute of these kernel weights, the kernel activations, to make this symmetrical. And we have a weighted sum here that we also learn the weights for. And those weighted sums are enforced to be positive, or the weights are enforced to be positive. And then finally, we have a output activation, which is the negative exponential, because we want to have a high score when we actually know we can step well, and a low score when we cannot. And we can train this with very few examples. So we just manually label height maps, just crudely drawing on them with the GIMP or Microsoft Paint or whatever. And yeah, we trained these particular kernel weights in just 20 manual labeled examples, and they also train very fast. So this is trained in 30 seconds on a just regular household GPU. And then once we have these things, we can actually use them for planning. How we do that is we maintain two separate collision worlds for the body and the reachability volumes. So on the bottom left, you can see the world for the body collisions. Of course, there you want to have the full collision world because you want to avoid hitting the wall, hitting stair risers in this case. And what's colored black here is geometry that is considered unsuitable for footholds. So yeah, you check the body for these collisions, but when you actually check the reachability for these collisions, you take those parts out, because you do not want to have your robot walk on a wall. You don't want to have it try to step onto the stair risers. Yeah, and that's how we integrate the foothold scores into the actual planner. Now to the planner graph, I mentioned that we do a bunch of things to make it a bit faster and work better in the real world. For graph expansion, instead of just when we draw a new sample, adding it to the graph and then only checking it when it's part of an actual path query, what we do is when we draw a new graph node, we select a random other node in the graph, do an A* query to get the optimal connection between the two, and then check those edges for optimality. The reasoning behind that is that there will be some edges which are just better in general because they kind of shortcuts. For example, here, if you see ANYmal here in this left corridor and it wants to go to the top right, the shortest way would be shortcutting through the wall, right? And if you never check these edges, a lot of these will just accumulate. And then when you actually want to plan, it needs to check all these edges. But when you already do that while sampling, you can avoid accumulating all these edges, which leads to a slowdown later on. And then the second thing we do is, I mentioned, we sample poses in a kind of smarter way. First of all, although our collision checking is performed in full 3D, so all the roll, pitch, yaw, and height, X, Y, and everything, we know that we have some constraints because the feet always need to be in contact with the ground. So we actually first sample in 2D, then augment it to a 3D pose with map information, put some additional noise on it, and they get a much higher hit rate with our samples than just sampling from a regular 3D volume. And lastly, we adjust the sample probability based on the existing node density. So you can see in this bottom right part that in this wide open space, we have lots of nodes because it's just very easy to get a hit. But in this very tight space in the bottom left, it's very hard and there are a few nodes. So we actually want to focus sampling here. And that helps a lot planning through narrow spaces because the sample actually tries to go where it's difficult. And then once we have all together, we can plan upstairs. This is in simulation, of course. But yeah, it just shows that even though we have these kind of what would traditionally be considered untraversable lines here, these stair risers, the method can still plan over it and we can subsequently follow it. And then again, simulation, but this time very narrow spaces. So this is really just barely the size of the robot, this corridor, yet the planner can plan very fast and kind of go through there in a very agile manner and negotiate well. But of course, you always have to go to the real world, otherwise it doesn't count. And this is again kind of a somewhat narrow space in the lab. Just the robot again planning. It's everything on the robot, mapping and planning and everything is on the robot, and it can negotiate that as well. And finally, because we say we do planning over challenging terrain, we put some obstacles in the lab. And again, the robot can plan over it just well and then follow the path just fine. And again, there's no pre-mapping of the environment. It's just built while the robot is moving. So you have missing information. You have a lot of noise in the map just because you have state estimation noise. But the robot or the planner can handle all of this, and it produces a feasible path which the robot can follow. Of course, all of this is still in the lab, and really you want to have this be useful in the real world and in more difficult environments. And this brings us to the DARPA Subterranean Challenge, where we also deployed this planner. So these are just some samples from testing before the challenge. But then last month, we actually went to the actual DARPA Subterranean Challenge. For those who don't know, DARPA is a governmental research funding agency in the US, and they sometimes do these robotics challenges for various things. This time it was for underground exploration. So the idea was there's lots of tunnel systems or urban underground systems and cave networks which need to be explored, are sometimes dangerous. You don't want to send humans in. So you want to have a robot go in and explore this. There were 8 system teams that participated in this challenge. We were part of Team Cerberus, and there were a bunch of notable labs and research agencies there which competed. 6 of those were actually funded by DARPA. So in the run-up to the challenge, they already got funding, and then the 2 bottom ones, they just had their own money and were significantly less well-funded than us. Team Cerberus, who are we? At the finals, it was 3 labs. It was the Autonomous Robots Lab, formerly from University of Nevada, Reno, now in Norway at NTNU. And then from ETH, we had the Robotics Systems Lab and the Autonomous Systems Lab. We had a few other contributors to Team Cerberus, none of which could make it to the final challenge for various reasons, but still important since they're part of the team to mention them here. And for those who don't know, we actually ended up winning this whole thing somehow. Still a bit unbelievable, since personally I could not have considered us being at the top somehow. But in the end, very happy that we won this. And as an interesting side note, this was the ranking of teams after the first qualification circuits. We were actually rated bottom of the funded teams. And also the other lower ranked teams all performed better than the high ranked ones. So somehow it all got turned upside down in the finals, which I found very interesting. Then the actual final event was in the mega caverns in Louisville, Kentucky. So they are a former underground limestone quarry, where they just blasted huge amounts of rock out of these caves. And then it got turned into a kind of a private amusement park in the 80s. And now they just had huge space to build something in there. And they actually built a complete course by hand. So it kind of, if you know theme parks and they build these kind of artificial environments, the worlds, that's kind of what they did there, just for us to send robots in. And it was really impressive what they did. So they had really narrow spaces and it looked really realistic. They built all the 3 subdomains, the tunnel, urban, a cave. They built a subway station and also had very narrow spaces, but also wide open spaces in these natural caverns. And the idea in the challenge is you have 1 hour to find as many artifacts as possible. You don't know the environment beforehand, but you know what the objects are you're looking for. So like it drills, a backpack, and a bunch of other things. And the main constraint is that you only have a single operator for all robots that you send in. And of course, no humans are allowed to enter. So yeah, the main challenges are autonomy, because one person needs to control all these robots. And then also communication, because in these very rocky environments, Wi-Fi and all wireless communication breaks down very quickly. So those were the main challenge in terms of operational space. And then for the robots, of course, this rough terrain is very narrow and tight. But yeah, a bit more on that now. The technical solution that we deployed on ANYmal, we also had drones, but I'll be speaking about ANYmal. We modified the planner that I just presented a little bit. The main changes, we use a learned motion cost, which is an idea we took from ETHZ, where you train a neural network to predict motion costs based on the local terrain. So you have take the local terrain patch around the robot and the command that you want to give to the robot or the motion direction. And this network then outputs a risk of this motion. It outputs the time cost and the energy cost. And then we use that to restrict some of the graph edges. So instead of doing classical edge validity checking, we use this motion risk to check validity of edges. And then also Lazy PRM star is an optimizing planner. So we put both the motion risk and the time cost in the cost function to get a better cost or better paths than just using shortest path. How this was embedded into the rest of the control or the autonomy stack. At the very top, we have GB Planner, which is a exploration planner, which tries to maximize information gain in a global map. So it has a volumetric map from Vox blocks. It knows the space that it hasn't seen and always tries to go where it hasn't seen much yet and try to maximize information gain. Of course, the global map is fairly coarse, it's 20 centimeter voxel size. So it is not able to represent the terrain in enough detail. So we need a local planner afterwards to follow this global path. How this works is it just tries to always go to the farthest away post in the global path. So in a way, it functioned as a glorified path follower, but much fancier than just a regular path follower. Also, the local planner can trigger global planning. So when the local planner realizes, nope, what you gave me doesn't work, it can feed that back to the global planner for it to replan and then find a different path. And then once we have a local path, this can be followed with a path with an actual path follower, which gives velocity commands to a locomotion controller. And just to make sure this is the part we're talking about, the local planner, which I presented previously. And now we'll be looking at some snippets of data from the actual competition. So this is what we're going to be looking at, this top-down view of the robot, ANYmal here in the middle. What's mostly interesting here is the local path, which is what my planner produces. Then these green arrows are the global path, which is the reference for my local planner. Then, of course, we also have the elevation map in these white and black colored grids. Actually, this shouldn't read traversability. This should be Foothold score. It's just force of habit, my bad. And then we also have these green dots, which is the global map, which is just a bit for reference, what the global planner sees. And then at the bottom, we have camera feeds from our artifact cameras, which is just a bit for you to understand what the environment looks like. Now, first, let's start off with negative obstacles. As I mentioned before, they built an entire subway station platform underground, which, of course, since it's a platform, has just mind the gap, don't fall down. It just has this sharp drop. Since the exploration planner is kind of optimistic in trying to find new and unexplored space, it likes going off of these edges. So it was up to the local planner to actually realize that that doesn't work and prevent it from falling down the step. Again, it's like if the global plan does not work, it's not possible, the local planner feeds that back and triggers replanning until we eventually find a new path that is actually followable by the robot. So just wait a few seconds because soon we'll go to the left, and there you can see how the cost function guides the path actually around this edge to have it safe, but at the same time also fast, and follow this path nicely and prevent it from falling down a bunch of times. Of course, this also works for positive obstacles. So in this case, we have these orange traffic cones here, which are untraversable, but in the global map look like the robot can go through. Again, the local planner stops it from running into it, triggers replanning, and we can successfully go around this. Also in narrow spaces, this is it walking through a door, which is not much wider than the robot. This might seem trivial to you. And also in these wide angle cameras, it always looks a bit wider than it actually is, but it's actually a bit kind of a challenge to fit through there. And also here they have these vertical poles, which the robot has to do some slalom around to not get stuck. And yeah, it managed to go around beautifully and not get stuck, which is nice. And then finally, we have a little bit of everything. So this is a kind of a different view. Again, these green voxels are the global map. They're just here to give you a sense of scale, because as you can see in the camera feed, this is in the cave section. It is very narrow, it is very low. There is a ramp and there's uneven terrain. So pretty much a little bit of everything, but still the robot is able to go through, follow this path nicely. This is also an achievement for the locomotion controller, but it's also nice to see that the planners actually go through and produce something sensible. And as you can see here, this little glow cube, that's actually an artifact which we found up those slopes and helped us win the challenge. And this is the same thing again, just as the view that we're used to now, or you were used to previously. Again, the elevation map. What you can see here actually is that because these environments have such a low ceiling, you actually have plenty of artifacts in the elevation map, because the elevation maps can't represent overhanging obstacles. So if you actually put ceiling points into the elevation map, you get a whole bunch of noise. But luckily, we were able to still plan around that. And then that's it from my side. I'll leave you with this of 15 minutes of fully autonomous exploration during the challenge. I'll just leave this playing while you can ask me questions if you have some.
Thank you, Lorenz.
Oh, one thing, the code is actually open source. I forget that every single time, but you can go check it online.